Hi everyone and welcome to the channel. In this video we are going to address one of the most commonly asked questions by beginners is how to get into data science. As we all know, data science is one of the most fast-growing domains, and the thing is that every year we get overwhelmed with new technologies that appear, especially those that are related to generative AI. There is a lot of hype going on in data science, and most beginners don't know where they should start. And I'm going to make a series of videos dedicated to this question, where in each video I'm going to discuss one of the key domains in data science and the skills that beginners should prioritize that will help them get into the data science field and get their first job. Let's get started. Before going into the details, it's worth noting that data science demands a diverse skill set and diverse competences across different domains. Personally, I like showing a Venn diagram that perfectly visualizes the three main areas used in data science. Let's have a look at it. Here's the Venn diagram. As you can see, data science lies at the intersection of three key areas: mathematics, computer science, and business expertise. While all three components are essential, I recommend that beginners concentrate primarily on the first two. The reason for this recommendation is that a solid foundation in mathematics and computer science is essential for any data scientist role. Meanwhile, data science is applied across a wide range of domains, including banking, e-commerce, supply chain, healthcare, self-driving cars, and more. As a result, the specific business domain you work in may change frequently throughout your career. And while it's still valuable to invest effort in understanding a particular business domain, this factor is often variable. Therefore, I strongly recommend prioritizing mathematics and computer science as core skills, and these two areas will be the primary focus of this roadmap series. A natural question that arises is that, can I train machine learning models without knowing math? In reality, you can. Indeed, there exist numerous high-quality tools like scikit-learn, Optuna, TensorFlow, PyTorch that allow you to train and use machine learning models for predictions. And the question is, why should I even bother learning all of this math if I have these amazing tools? Understanding how algorithms work under the hood helps you make better informed decisions about which algorithm to choose for a given task. Moreover, you have a better sense of advantages and disadvantages when using this or that algorithm. You get a better scope for which the algorithm should be applied, and you can also debug the solution more easily and better choose the necessary parameters for the algorithm. In some situations, you can even adapt or re-implement the algorithm that will better suit your needs. Furthermore, many algorithms are built upon one another, so grasping the fundamentals of basic algorithms will make it easier to understand more advanced ones. Finally, in a data science career, it's often necessary to review recent scientific publications. And as a general rule, machine learning articles and papers frequently contain numerous mathematical notations and formulas. To fully understand their context, a strong foundation in mathematics is essential. Given the points I have outlined, I hope the importance of learning math is now clear. Next, let's discuss the specific mathematical skills you need to develop as an aspiring data scientist. It's time to get into the depth and look at concrete math domains and the concepts that beginners should study in order to get into data science. The first thing we're going to look at is calculus. Calculus is a vast field encompassing an abundance of beautiful equations, theorems, and concepts. Without this knowledge, understanding the inner workings of basic machine learning algorithms would be nearly impossible. The good news is that data scientists don't need to know all of it, as only a few key concepts are used in the most important algorithms. And the diagram on this slide illustrates the essential knowledge to focus on initially. Many machine learning algorithms are based on optimization problems where the goal is to find the minimum of a function, typically through the calculation or derivatives. While integrals are not as commonly used in machine learning, they remain very useful in statistics and probability theory, another important area we'll focus on later in this video. In simple terms, integrals are the inverse operation of derivatives. And as it turns out, integrals and derivatives are closely linked to each other, and many theorems rely on both to prove key concepts. I would say that reaching a point where you understand how derivatives are used will help you to grasp the stochastic gradient descent algorithm, or SHD. It is a fundamental method employed by most machine learning algorithms to update the weights of the model so they learn better. And while algorithms are constantly evolving and many scientific papers rely on advanced mathematical concepts, they become much easier to understand once you have a solid foundations in the basics of calculus. Another important domain we're going to look at is linear algebra. It is another key area in mathematics that focuses on vectors, vector spaces, and linear transformations. In data science, data can be represented in various formats, but ultimately it is converted into vectors of numbers that are fed into a predictive model. Vectors are also used to compare similarities between objects, estimate correlations between variables, perform feature engineering, update model weights, or encode the semantic meanings of words. And given their broad range of applications, it's crucial to study vectors early on. The next important topic is matrices, which can be viewed as a collection of several vectors stacked together into a table. Matrices are used to represent tabular data or graphs. They are widely used in neural networks, where a layer of the network can be represented as a matrix. This matrix representation enables faster calculations, as many mathematical approaches are optimized to work more efficiently with matrices than if the same calculations were done without them. Another important application of matrices is solving systems of linear equations. Each such system can be represented as a matrix equation that you can see here. Given this, there are several methods to solve the equation based on matrix properties such as multiplication, finding the determinant, or calculating the inverse matrix. Finally, matrices can not only represent tabular data, but also be used to compress it through matrix decomposition. This process involves representing the original matrix as the product of several smaller matrices. This method is particularly popular in recommender systems, where relationships between a large database of users and products can be stored as a combination of smaller, more efficient matrices, as you can see here, where we decompose this larger matrix into multiplication of these two smaller matrices. Now let's go to statistics. In data science, exploratory data analysis is a crucial part of data analysis involving the exploration of data, detection of anomalies, formulation of assumptions about relationships between variables, and studying their impact on the predictive variable. All of this requires a strong foundation in statistics. To effectively describe data, one must study basic descriptive statistics and methods for visually representing data. This is one of the simplest yet most important areas in mathematics. Probability theory is another fundamental building block that appears in many areas of computer science. In the context of machine learning, there are numerous metrics used to evaluate the quality of an algorithm, many of which are based on probability definitions, such as precision, recall, and ROC AUC. There are even probabilistic models such as naive Bayes algorithm, which is used for classification tasks. Furthermore, classical probability theory includes various types of data distributions, with the normal distribution being particularly important. You can see its form right here. Its significance cannot be overstated, as it can be applied to describe a wide range of real-world processes. Finally, the introduction of central limit theorem and confidence intervals provides a foundation for understanding the next major topic in statistics, which is hypothesis testing. A/B tests, which are based on hypothesis testing, are another important topic in data science. The goal of A/B testing is to determine whether there is a significant difference in a given metric between two groups of objects that were initially split based on a specific criteria. For example, imagine a supermarket conducting an experiment to determine whether sending SMS messages to its customers will increase the total revenue. To start, the entire customer database is taken and randomly divided into two groups, ensuring there is no existing bias. These groups are labeled A and B. Then the marketing campaign begins and the supermarket sends SMS messages to all customers in group A, while those in group B receive no communication. After an initially defined period of time, the revenue is calculated for both groups. If there is a significant difference in revenue between the two groups, considering the initial settings, then we can conclude that sending SMS messages has an impact on the generated revenue. Of course, this provided example is quite simplified, as the actual science behind A/B testing is much more complex. Nevertheless, hypothesis testing is a fundamental component of A/B test, as it explains the underlying logic and offers various methods for conducting A/B experiments in different scenarios. Finally, let's have a look at discrete mathematics. In my personal experience, discrete mathematics is the easiest branch of mathematics to study compared to the previous ones. As the name suggests, discrete mathematics studies mathematical structures where the variables are discrete, in comparison to calculus where variables were continuous. Many books and courses introduce discrete mathematics by starting with set theory, which makes sense because sets are used almost everywhere to formally define other structures, express complex mathematical constraints concisely, and formally prove various statements and theorems. Additionally, the notation used in set theory is widely adopted in machine learning papers, as you can see at the example on this slide. I took a part of the algorithm which is defined in one of the reinforcement learning papers, and you can see that all the notation here is based on the set theory. Now, the next important branch is relations and functions, which study the relationships between elements of sets. While it's rare to encounter a direct application of relation theory in real-world data science problems, its knowledge still remains valuable. This is because many proofs in other domains, especially in graph theory, can be simplified by applying concepts and properties of relations. Next, Boolean algebra deals with the Boolean functions that operate on binary variables. It is another key area. The interesting thing is that it would be impossible to imagine modern computers without Boolean algebra. In fact, at a low level, computers only operate with 0 and 1s, and all computations are carried out based on the principles of Boolean algebra. Knowledge of Boolean algebra helps in understanding logical conditions and operators in code, for example, filtering data in SQL and other languages using logical operators, optimizing queries, and performing data processing. Combinatorics is a branch of mathematics focused on counting and arranging objects within finite data structures. This knowledge is useful for estimating how many samples or trials are needed to conduct an experiment, optimizing sampling techniques, or dividing objects into subsets or computing the number of possible paths in a graph. While tables remain the most popular format for data representation, they cannot directly store the relationships between objects. And this is where graphs come into play. A graph is a data structure consisting of vertices that represent objects and edges that store the relationships between them. Depending on the type of edge, it can either indicate the presence or absence of relationship between a pair of vertices or store a weight that signifies the strength or weakness of the relationship. This seemingly simple structure is supported by an entire field of study called graph theory. Graph theory explores various types of graphs and their properties, such as grouping vertices into components based on their connectivity with other vertices, or finding the shortest path between two vertices. An obvious application of graphs is the analysis of a social network. A network of people can be viewed as a graph where each vertex represents a person and the edges connecting it lead to other people that the person knows. While this is the most commonly used example when discussing graphs, their application scope is vast and extends beyond social networks to any domain where relationships between objects exist. In particular, graph theory is widely used in logistics optimization problems. And here in this slide, you can see an example of a graph representing interactions within a data science team. And in this example on the slide, you can see a graph representing interactions within a data science team. The vertices represent team members and the edges indicate the level of interaction between them. So you can see that, for example, here Jack interacts a lot with Elisa, Here it's indicated by the age with weight 4, while, for example, William, a data engineer, interacts not so much with Oliver, where the age has only a weight of 1. So this is one of simple examples. Now, an important question: should I study proofs or theorems? This is a common question that arises among math learners. All 4 of the math blocks we have discussed contain numerous statements and theorems that have been rigorously proven. The challenge is that fully understanding the logic behind a proof often takes a considerable amount of time. So, is it really worth investing time in proof analysis? In my personal experience, analyzing and deeply engaging with proofs played an important role during my university studies. On the one hand, it's clear that after graduation, I don't actually remember most of the proofs, something that is completely normal, as our brains tend to forget information we don't frequently revisit. On the other hand, being able to understand the reasoning behind almost every math theorem I encountered in the past helped me become less intimidated when facing unfamiliar statements in new machine learning papers. And it also sparked a desire to explore why those statements are true. Additionally, this approach promotes abstract thinking, which is important for success as a data scientist. So in the end, my answer would be yes. You should go through the proofs of mathematical theorems you encounter when studying basic math to become a data scientist. Of course, there can be other cases. For example, if you don't have enough time to study, I would recommend you to focus on the most important proofs or just to try to understand the deep meaning behind the theorem statements. But if you don't enjoy at all studying proofs, you should ask yourself whether you truly enjoy math and if you are certain about pursuing a career in data science. As I told you before, it's a very demanding field. In this roadmap, we have explored the 4 most important branches of mathematics for data science. While the list of terms of concepts could obviously be expanded even more, I tried to focus on the most essential ones. And you have to understand that having developed solid math foundations is a significant advantage, because you can grasp new ideas and algorithms more quickly, and this is where the true value of a machine learning engineer lies in today's world market. And that's it. It was the first part of the roadmap of becoming a data scientist. In the next videos, we'll explore other key domains and technologies you need to master to become a data scientist. Thank you for watching this video until the end, and see you next time. Bye.